My name's Kyle. I work with Oxide primarily on maintaining our packet transformation engine, OPTE. And what I'm going to talk about today is just a fairly simple utility we put together to make exposing nested enumerations and other error types up to dtrace scripts a lot more accessible and a lot more performant for us. So to give some context, OPCE, the Oxide Packet Transformation Engine, is our packet processing stack for virtual machines. Fundamentally, any packets which leave an instance to talk to another instance, or to talk to the outside world, or even for one of our internal services to talk to the outside world, these packets have to be encapsulated by OPCE or decapsulated if they're received. And to do that, we implement it as a kernel module within a Lumos. dtrace itself is a fantastic tool here, and it gives us an incredible amount of value because otherwise we would have a lot of difficulty in being able to actually instrument and inspect all of the steps which OPTE is taking. So to do this, we make use of a lot of statically defined tracing or STT probes, and we use these due to several reasons, down to Rust in particular, but also to several events. So Rust's name mangling, as you've seen come up in several of the other talks so far, and also unpredictable inlining can make it hard to know when specific functions that we're looking for are happening. So we use STTs a lot to make sure that we always get we always have probes firing when we expect them to, and for the events that we really care about. In particular, we use this to show and to demonstrate the final decisions made by a port as to what should be done with a packet, to show the incremental effects of like per layer processing and packets, what decisions are being taken every time we go through, the router, NAT, the gateway, the firewall, etc. But we also use them to show parse failures and serialization failures, which are absolutely crucial for debugging certain classes of issue which come up when developing this sort of thing. So it's no understatement to say that dtrace is, absolutely key for debugging and developing this piece of software. When it comes to the sorts of information we want to attach to these STTs, though, like here's an example of a result type for basically the final decision that is made for every single packet. And if you've done a lot of Rust programming, this will look quite familiar, this structure, this idea of having nested enums, which allow us to trace effectively trace a series of decisions made about something, along with like additional context along the way. And it gives us a very strongly composable way of expressing errors and results. When it comes to parsing errors, this gets considerably deeper. We have, deeply nested enums here. We have leaf nodes containing additional data pertaining to the variants of interest that we care about. And while this makes it easy to deal with these values in code, and it makes it easy for us as humans to look at them when they're printed out in debug format. However, around February of this year, one of my colleagues, Matt Keacher, was doing a bunch of additional flame graph work on one of the sleds, and noticed that in amongst the traces he was taking, here is XERX, which is basically the method which is called whenever a packet is received on the network. To give some context, the packets we're looking at here are ones that we don't care about and that we want to drop because they're not encapsulated. The open question that Matt raised was, why are we spending so much time here in this bad packet parse probe function? And, there are two instances of this badness going on here, one of which is this alloc format. So that's the debug representation of an error type being called. As it turned out, this one was just a call to basically, push the messages onto var ADM messages where the format call had fallen outside the macro. No biggie, easy enough to fix that. However, we had a more significant problem here, which is in the STT probe that we had set up, bad packet parse. So to make this usable from within the STT context, one of the things that we had to do was was effectively to print format these values out. And as you can probably expect when you're doing this on a per packet basis for the packets you don't care about, that's actually extraordinarily expensive. And you can see here that it's, we're spending more time printing out these values for probes that we're not necessarily caring about or listening to in total than we are, say, actually parsing the packet and making a decision on the fact that we should drop the thing. Not even the fast path is immune from this. So the first type I showed you, which wasn't too deeply nested, we're still paying some of that tax here because we have it been inlined out here. But we do have another call to the basically a helper function wrapping one of our SDTs, which requires, again, that we express the decision made for this packet in a format which is, readily amenable for use in an SDT or a dtrace script, I should say. So fundamentally what's happening is that, calling SDTs themselves is basically free. As you've seen, they're replaced by NOP instructions, or they're set as NOP instructions when you load the kernel module in. And when we register those probes, those are replaced with jumps to, yeah, exactly. Brian, I'll come on to that shortly. Unfortunately, getting data into the right shape for these SCTs is not a free operation, and we do not want to have to think about paying this price for every single packet that we admit. Part of the problem, and it's a good problem to have, is that idiomatic Rust errors really encourage us to store and think about error chains in this way. Not just for handling them in the program sense, like having these nice composable configurable errors. But as operators, these give us a chain all the way down to what went wrong in the first instance, as well as potentially every layer of the stack that they happened in. These root causes are useful to have, and they're not necessarily repr friendly, particularly if you have an error type which comes from a third-party library. When you cross over that boundary, well, you can't even decode that manually in your D script in a consistent way without, invoking nasal demons. It's not a nice position to be in. And even if we did control every aspect, manually decoding these things is going to be very tricky, very brittle, and very error prone. So just going back to thinking it through. When we take an example of one of these decisions that we've made, process result drop, in this case, this has all the information we need to understand why individual packets are being dropped. So it's unwieldy, but when it comes down to how we want to handle this, so as we've just discussed, manually decoding all this information and dtrace is out of the question because it's extraordinarily brittle. And, when we cross into another library's error type, we have no control there. We could flatten out everything we have within our own program into a sort of God error type. The problem then is that you lose a lot of this nice composability, and you spend a lot of time writing automated conversion, like from and into methods and so on. And because we're in the kernel, we don't have as enabled. So we can look at this from another perspective. If we draw everything out, well, we're computer scientists, right? This looks an awful lot like a tree because it is. More importantly, this is a tree of strings and leaf nodes who have additional data. And at least for the error types that we've constructed here, we have bounded depth. And this gives us something that we can maybe use to try and get all this information up to a consumer while doing the minimum amount of work possible. So DError itself is a very simple trait. Basically, we just ask that any form of result or error can provide a label for itself. It can tell us whether or not it has a child. And if it is a leaf node, then it can fill out some amount of leaf data attached to this label block. And when we're filling a label block, all we really do is recursively say, okay, I have the current error, give me the discriminant. Does it have a child? If so, push that label on, rinse and repeat, push that label on, push that label on. And when we hit a leaf node, we fill out the data. So the way we handle this is we have a compile time fixed storage, that's const L. And at runtime, this more flag is set if we ever, encounter a chain which is deeper than L. And just to make things really simple for ourselves, we do still have the trapdoor of if we have our own string and we're willing to play one or two uh, one or two unsafe gains to make sure that that string lasts longer than the label block itself and does not outlive the SCT context, then we can pass that information up and just fill that in as one of the labels, as long as we correctly make it a C string, of course. So given that we have a lot of error variants and a lot of nested types, one of the ways that we handle this is we've put together a simple enough proc macro, which simple enough proc macro derived DError. Fundamentally, all this really does is it goes down every single variant we have and converts, a C string representation for the variant's name and provides a child walker for any of the shippable variants we have automatically. If we have something that's not actually containing another error that we want to parse or handle, we have a wee leaf annotation here. And in practice, one of the things you'll notice from the, first slide where we looked at the error types is that bad error was originally a string. Having this sort of enabled and empowered us to actually automatically derive all of this and get that additional information without doing string format. So, unfortunately, handling leaf data within the proc macro could be done, but we took the decision just for expediency to explicitly make this a user choice, really. In practice, it works, but the dtrace needed to handle this sort of variable length thing is slightly awkward, and I'm probably doing it wrong to some extent, and have been doing it wrong since March or February. But the useful thing is that it does not fundamentally change on either the call sites that we're interested in, and it does not change on, pardon me, it does not change the call sites we're interested in, and it does not change with respect to the type of enumeration that we're actually working with. So this is a pattern that's more widely reusable for no matter a pattern that's widely reusable no matter which error type we want to introduce down the line. If we want to, create something new that we hadn't cared about at the time. And it looks slightly different from what Rust programmers will be used to with the debug format, but the output itself is readable and it does capture the full chain of errors all the way down to the root. So here you can see that this one does include the old string version before that had been migrated over. But you can see that it just sort of proves out that, we can have leaf nodes, we can insert data. If we have a custom string, we can pop that on too. No biggie. Easy ways to solve problems that we want to kick down the road. So I guess practically, finally, did this solve the performance problems we were having at the time with this? And the answer is, quite a convincing yes. So this is just for the unexpected packets that we were dealing with, the ones we didn't really care about. We had, a mean 1.23 microseconds down to, around half that to process it here because we managed to get rid of this block here trivially and this block through all of this work. You can see here that the amount of time we actually spend, selecting this discriminant drastically smaller than either of these two blocks. And recently we did end up rewriting the parser stack within OPTE. So one of the things I was initially worried about when we did this work was that, if we were to hit an external library with more difficult boundaries or like hidden types private variants or so on, that we wouldn't necessarily be able to provide the functionality we need. As it turns out, converting the base parse error types from that library to match what we have here simply required is just to, fill out all of the C string variants here, and then the amount of implementation for the trace itself is absolutely minimal. You can see the output here is sort of as you'd expect. It tells us, we have this class of error. Here's the layer in which it was observed, and here's the actual error class that we're dealing with. So it's not a perfect solution. It was effectively built to solve this one performance issue we were having at the time. So if we were, to spend more time in this, it'd be an issue of thinking about how to better handle variable length data blocks or generic data. One of the things I was interested in upon revisiting this was the idea that we could maybe, encode the maximum depth required, the minimum depth required to capture the entirety of an error type within the DError trait using const generics, for instance, like that would give us the compile time assurance that a given label block is large enough. And if you care to look at the implementation, there's a lot of a lot of Dyn references being used, which I would prefer to remove since it does have a cost associated with it. But this is, orders of magnitude smaller. The main lesson of this talk is make sure your SDTs are REPRC friendly, of course, and make sure that your inputs are cheap. See also, there was a related OPTE issue on converting something that looked cheap into a different type that was friendly for an SDT, but it turns out if you do that enough times, then that gets expensive too. So make sure to feed your SDTs well, and your kernel modules will probably behave as you expect. Thank you very much.